Hi, this Jamboard session is about the triangle inequality for the bottleneck distance. Recall, if P and Q are persistence diagrams, a partial match is a bijection between a subset of P and a subset of Q. The infinity norm distance between points BD and B prime D prime is defined to be the maximum of the difference, absolute value of the difference in B values and the absolute value of the difference in D's. We also need the infinity norm distance between BD and its nearest point on the boundary on the diagonal, and that's 1/2 D minus B. Okay. Now, to define the cost of a partial match, so that's going to be Cm equals a maximum of 3 different values. The first value is the sup, or maximum, of the infinity norm distance between Pi and its matched points, M of Pi. Then we have the unmatched points in P. We want to take the sup of the distances from those points to the diagonal. And we have the unmatched points in Q. We want to take the max or sup of the distance between those points in the diagonal. So the cost function is the maximum of these 3 values. The bottleneck distance between P and Q is the infimum of the cost functions over all possible partial matches M from P to Q. Okay. Now, suppose we have 3 persistence diagrams, P, Q, and R. We want to show that the bottleneck distance between PR is less than or equal to the bottleneck distance between PQ and the bottleneck distance between QR. So this is a triangle inequality. Since this involves the infinity norm distance, let's warm up by proving the same thing, the triangle inequality for the infinity norm distance. So I'll write this in terms of x, y's, and z's. It doesn't matter that they're persistence points. This is just about infinity norm distance in the plane. Okay, so we want to show the infinity norm distance between x and z is less than or equal to that between x and y, and that between y and z. Okay, so let's start with the infinity norm distance between x and z on the left. That equals the max of the difference between the first coordinates and the second coordinates. Now, if we look at this, the max, and use the triangle inequality in each of the terms, we obtain this. So it's the max of, let's make the max of absolute value of x1 minus y1 plus absolute value of y1 minus z1. That's the first term, plus then the absolute value of x2 minus y2 plus the absolute value of y2 minus z2. Okay, that's by the triangle inequality for the absolute value. Now, if we look at these, look at the first term, and we have absolute x1 minus y1 plus absolute y1 minus z1. That will be less than or equal to the max of absolute x1 minus y1 and x2 minus y2. That can only get bigger when we take the max, plus absolute value of y1 minus z1. There. Now we do the same thing for the second coordinate. We replace absolute x2 minus y2 by the max of absolute x1 and absolute x2 minus y2 plus absolute y2 minus z2. So now, since we have the same maximum appearing in both, that's a constant. We can pull that out, take that constant plus the max of the remaining 2 terms, so we get max of absolute x1 minus y1, absolute x2 minus y2, and then max of y1 minus z1, y2 minus z2. That's just the infinity norm distance between x and y, plus the infinity norm distance between y and z. So that's the triangle inequality. Now we want to simplify the proof a little bit for the bottleneck distance function. And the way we'll do this is we'll, sleight of hand, we'll include all the diagonal points in the diagrams. So then when we have the distance to the diagonal of a point, of an unpaired point, it will now be to a point in the other diagram. This means we can only need to think of 1 sup instead of 3 different sups when we look at the bottleneck distance. And since the number of off-diagonal points is still finite, sup in the definition is still over a finite set. This simplifies the cost. The cost function now looks like the sup over all pi of pi minus its matched point, and some of these matched points are now on the diagonal. Now, since P, Q, and R are finite off the diagonal, there are partial matches, now they're complete matches, M1, M2, M3, such that the following is true, such that the cost of M3 is bottleneck between P and R, the cost of M1 is the bottleneck between P and Q, and the cost of M2 is the bottleneck distance between Q and R. So now we also see that if we have M1 is a match between P and Q, and M2 is a match between Q and R, M1 composed with M2 is a match between P and R. Now, let's start with M3. Since M3 is optimal, it's the best possible match between P and R, we have the sup of Pi minus M3 Pi is less than or equal to the sup of Pi minus M2 composed with M1 of Pi, because M3 was optimal. Okay, now let's apply the triangle inequality. So we're going to apply it to Pi minus M2 composed with M1 of Pi. We're going to insert an M1 Pi, so we get Pi minus M1 Pi in the first term, and then M1 Pi minus M2 of M1 Pi in the second term. Well, the first term, that's just the cost function of M1, because M1 was chosen to be maximal. That's the bottleneck distance between P and Q. Now on the right-hand side, notice that M1 Pi, that covers all the points in Q because M1 was a match between P and Q. So now what we have is a match between points in Q and M2 of points in Q. Well, what is that? That's the sup of QK minus M2 QK, where QK is a relabeling of the points in points M1 Pi. So what is this? This is the cost of M2, but the cost of M2 is the bottleneck distance between Q and R. So we wind up with the bottleneck distance between P and R is less than or equal to the bottleneck distance between PQ plus the bottleneck distance between QR. So with properties 1 and 2 from the previous session, this proves that the bottleneck distance is a metric on a set of persistence diagrams. So we'll use this as we go on in the course. And that's the end of this session. Thank you.